Okay, well, we're starting a little late on the recording, but just to quickly summarize what we're doing, we're talking about power. We're doing a simulation study where we are looking at the difference between two baseball teams, the Mets and Yankees, assuming we know their population parameters for number of wins in the season and the variability. So we're saying 85 for the Yankees, 80 for the Mets, standard deviation of 10. So we're simulating a Cohen's d of 0.5 essentially. We are going to try to understand how often we will be able to reject the null hypothesis that the two teams are equal given these population parameters. So when you want to generate random numbers in R, there's lots of great functions for doing this. One of the really nice things about R is it's really easy to do this type of thing. So there's a function called rnorm. So this will generate random numbers from a normal distribution. There are lots of these functions, like they always start with R. So like there's RUnif, which would just be a uniform distribution. That'll just give you a random number between 0 and 1. There's other distributions too. They always start with R and then the name of the distribution, and then whatever parameters you need. There are all these random number generators. So for rnorm, we need to know three things. We have n, which is the number of draws we want to make, the number of random numbers we want to generate. Then we need the mean and the standard deviation. If you don't enter those, it'll just default them to 0 and 1. But here we're using our actual population parameters. So what I'm also going to do is set a seed value before I draw my random values. So does anyone? Setting it's up there. Setting a seed value, essentially what that does is it fixes the random number generator. So it'll draw the same random numbers every time. If I don't do that, it'll just be totally random numbers. This lets me reproduce the slides. If I don't do that, essentially, I won't know what'll come out on the slides because it's going to produce random numbers that are going to be different from what I'm going to tell you. So this lets me know exactly what the random numbers are going to be. So I'm going to draw 100 random samples for the Mets with a mean of 80 and a standard deviation of 10, and then same from the Yankees with a mean of 85 and a standard deviation of 10. So essentially what I'm saying is these are 100 random seasons for both teams, and we're seeing how many games they both win in each of those 100 seasons, and we're going to compare them. So I could start by doing a t-test. And so here we see it's a large sample. So unsurprisingly, we're getting pretty close to the actual population parameters. We see the mean of X, which is the Yankees, because the first one is 85.14, so a little bit high. Mean of Mets is 80.8, also a little bit high. But we're rejecting our null hypothesis here. So we're getting a big enough difference that we're able to tell that they're significantly different given our degrees of freedom. Any questions so far? Okay, we can also check the Cohen's d. So again, I can, this is our sample Cohen's d, not the delta that we know about in the population. And again, we can see it's pretty close to the actual delta in our population. It's a little bit smaller. It's 0.46. The actual population difference is 0.5. So I rejected the null hypothesis. My Cohen's d is pretty close to what it actually is in the population. And what I really want to know here is what's the probability that I will reject the null hypothesis if I keep doing this over and over again? What proportion of times is the null hypothesis going to be rejected if I keep doing this procedure over and over and over again? So the way we can do this in R is with a for loop. And so now we're getting in a little bit more into the programming weeds. I'll show you what this looks like. So essentially what a for loop does is it says, I'm going to take some procedure and do it over and over and over again, as many times as I want. I could tell it how many times I want to do it. So the first thing that we need to do is we need to create an empty variable to save our results in, because it won't automatically do that inside the loop. So then I'm going to set my seed value again. So I'm drawing the same random samples. And the way the for loop works is you define a variable. Often it'll just be I, like the letter I for iteration. So then I'm going to say for I in 1 to 10,000. So this is saying I'm going to do 10,000 loops. I'm going to do this procedure 10,000 times. And then so each time I go through the loop, I'm going to generate 100 random samples for the Mets and 100 for the Yankees. Then I'm going to do a t-test and get the p-value here. And I'm going to save that as the I number element of this empty variable I saved before. So each time it goes through the loop, it's going to save my p-value and replace one of these missing values that I started with the p-value from the test. Is that clear? Does that make sense? Okay.
What is the NA?
So NA is placeholder for missing. That's just how you define a missing value in R. I could have put anything there. Just NA is just, NA is good because now I know if something doesn't work for some reason, it's going to return a bunch of NAs instead of actual numbers. So it's just, but yeah, it just means that's the R definition of a missing value. So now what I can do is I can look at the proportion of times we rejected the null hypothesis. So what this is telling me is in what frequency of cases was my p-value below 0.05. So using the prop table around the table function, which just gives me, it's a proportion table essentially. So this is the percentage of times I rejected the null hypothesis. So we see here I rejected it 94% of the time. That's our statistical power. So that proportion and the frequency of times I rejected the null hypothesis, that's our statistical power for this study. So any questions about that? This is how you can simulate, a very easy way to simulate statistical power given some population values or something like that. So, you know, you don't have to do simulation studies for t-tests. There's lots of, there are more analytical ways you can do this. So in R or in G, in R, there's a package called Power, which is very similar to what you'll see in the G Power program. So there's a bunch of different functions here. And for any of them, they take 4 inputs, sample size, effect size, alpha level, and power. Sometimes these are broken down, like in Anova, like you say the number of samples per group and then the number of groups or something like that, but it's still sample size essentially. And so what you have to do is you specify 3 out of these. You can specify any 3 in these functions, and then the 4th one it'll give you. So as long as you know 3 of these, the 4th one is determined. So that's what these functions do. You can leave any one of them out, and then it'll tell you what the 4th one is. And so the power t-test function will do this with t-tests with equal sample sizes. There's a slightly different one when they're unequal sample sizes. So here I'm entering all my population values. So my sample size and my Cohen's d of 0.5, and then my significance level 0.05 into this. So I'm leaving out what the statistical power is. And so then it's going to give me this output. And then so here it filled in the power. And you see it gives us a very, very, very similar result, 94%, off in the 3rd decimal, which will happen with a simulation study because it's not exact. So any questions?
So effect size is defined as Cohen's d.
For the t-test, yeah. There's different effect sizes that you'll use for different situations. But for a t-test, the effect size is Cohen's d, yeah. And so it's actually technically delta because it's the population effect. Cohen's d is a sample estimate of the population effect. There are other things like Hedges G you'll see, or Glasses delta. Those are also slightly different versions of the sample estimate, but it's technically delta, yeah. Right. Any other questions? So now let's take a look at what would happen if instead of using 100 seasons per sample, I only use 10. So I'm looking at a much smaller sample of seasons that I'm drawing from. So here, instead of n equals 100, I'm doing n equals 10. And I'm doing the same thing. That's the only thing I've changed here. And this is my simulation study again. And here what we see is our statistical power dropped a lot. It went from 94% to 19%. And here we can see the same thing if we do it using the power function. And so this is an example of what happens, of how sample size influences power. And actually, Michelle, you'd asked me a little bit about this too, because in the homework, there was a situation where maybe you had a fairly small effect size, but you got a significant value. That can certainly happen. So let me actually, I wanted to demonstrate this because it wasn't in my slides. So I can go into my R program. Oh, I think I don't have power and install. I need to install some packages on this computer, but that's okay. I can do this in a regular R script. So how do I need to write it? So let's say we have a huge sample size, right? We have a massive sample size. But then we have a tiny, tiny effect size, right? Really small effect size. So huge sample, tiny effect. and then significance level is 0.05. I'm pretty sure we're going to have very high power here. Did I write it wrong? Oh, I didn't write it. So it's not super high even, but it is pretty high. So we have a 61. There's a 61% chance we're going to reject the null hypothesis with a tiny little effect, just because we have such a huge sample size. So this is one of the reasons. Another one of the faults with p-values is that, do we really care about an effect that small? No, right? So like when you have a big sample, like p-values aren't that informative, because you're almost always going to reject the null hypothesis in a case where you have massive samples. So we tend to be very reliant on them for a lot of reasons, and it's becoming a little bit less so. But this is one case where they fail us in not just in the direction of lack of replicability, just in terms of like, this is a true effect, so small that we don't care about it, and we're gonna find it if we have a big sample. So any questions about that? Does that sort of clarify the question that you had a little bit, Michelle, too? Okay. So that's sort of what you'd call like an analysis for power. A lot of times you'll see that done as a post hoc test, which is actually sort of not really a great thing to do, because post hoc tests use observed power instead of population power. Not going to get too much into the philosophy of that right now. What's more common and what you'll see when you're planning a study is what's known as an a priori power analysis. So the difference in an a priori power analysis is that you're trying to, instead of trying to figure out what your power is, you're trying to figure out what sample size you'll need given an effect to achieve a certain level of power. So you're inputting sample size alpha and effect size. I'm sorry, you're inputting effect size, significance level, and power, and you're getting the sample you'll need. So this is a way of planning how big a sample you'll need in your study. And so this is sort of the most common type of power analysis you'll see. It's a little bit harder to simulate this. Like you can do it, but like it takes a lot more steps. So I'm not going to go into that. But we can just use the function here. So let's say that I wanted to find the sample size I need to have 80% power to reject Cohen's d of 0.5. We see that I need a sample of about 64 per group. So I don't need a full 100 seasons to have 80% power. Any questions about that? Make sense? And so I could simulate the result I got to show that it's true. If I wanted to actually try to figure out what that value was, the simulation would be more complicated, but I can verify it to get the result. So I could plug in samples of 64 and into my simulation, and we see that my power was 80% here in my simulation as well. So it's the same result. So another type of power analysis you'll see sometimes is a sensitivity analysis. So in a sensitivity analysis, what we're trying to determine is the smallest effect we can expect to find with probability equal to our power given our sample size. So this is saying we know sample size, we know power, and we know alpha. So what's the effect, the smallest effect we can reliably detect with that probability? And so here what we're leaving out is effect size. So here I'm going to put in my sample size of 100, alpha 0.05. I'm going to say power equals 0.8. So this is going to return the effect size that I can reliably detect. And so it's about 0.4 here. So it's a little bit smaller than what I did in my original study. And that makes sense. I needed a smaller sample to detect my effect. With the larger sample, I can detect a smaller effect. Make sense? So for our purposes, what we're more frequently going to use in an Anova is the power Anova test function. So this is for one-way Anova. So what this takes is, it's a little bit, takes one more input, which also is the number of groups. And then it's the sample size for groups per group. This assumes that the sample sizes are equal per group. I'll show you a way to do it without equal sample sizes, but that's a little bit trickier. Then we're also going to need Cohen's F. So that's the effect size this uses. It uses Cohen's F. And then we have our significance level and our power, which are the same idea that we had before. So for me, it's easier to think in terms of eta squared than Cohen's F. I don't know why these functions don't use eta squared. It's a more common effect size that you'll see reported in literature. I haven't read many papers where Cohen's F is actually reported, but Cohen's F can be determined from eta squared. So another thing that I can do very easily, so another programming thing you can do in R is you can write your own functions. So what I did here was write a function that just converts an eta value to an F value, so I could input it here. And so the way you write a function, just without going too deep into this, is you name the function, and then you say, I want a function of some value. So this function is a special function. So eta is some variable that I'm going to input. Then inside curly brackets, I write what the function is going to do. So here I'm writing, I want square root of eta divided by 1 minus eta is my F. So that this is referencing this variable here, and then it's returning a new variable here. And then I have to return what I want the function to output. So what this function is going to do is it's going to take this, and then it's going to give me this. And so it's just going to essentially do this formula for me. Just a simple function to help me so I don't have to do the math every time. And so I ask you to write a function in the extra credit on your homework. It's a challenging one. Don't get too bogged down in it, but it's good programming practice if you give it a try. So here let's say we want to decide our sample size for an experiment with 3 groups, 3 equal size groups. And we want to be able to reject the null hypothesis with eta squared equals 0.1 80% of the time. So this is saying I want to know what this is an a priori power analysis. I'm saying I'm expecting my eta squared to be 0.1, and I want to have an 80% chance to reject the null hypothesis if that's the case. And so I'm going to just plug in my eta to F of 0.1 here, and you see that's going to actually give me my F value, which is reported down here in the output. And so the other thing that filled in there was the sample size. So it's telling me I need about 30 per group to have 80% power to reject a Cohen's F of 0.33, which is equivalent to an eta squared of 0.1. Questions? So when you're doing, when you're submitting a grant proposal or you're proposing a thesis or a dissertation that requires you run a study, a lot of times committees will ask you to do something like this so you can justify your sample size requirements to them, or to justify your sample size in general to them. So that's the most common type of thing where you'll see a power analysis like this.
So that means that you were ready before you do this, you run the eta program and get the value into eta, and then you, in other words, you've already generated the eta value.
So this turns it into an F value.
Right, but before you did it, did you have to?
So I'm assuming, so the point here is, like, I'm saying that, like, I think you're making a guess, essentially. You're saying that, like, I want to be able to detect an effect at least this large.
No, okay, that's not okay. In order to use eta to F,
Oh, yeah.
you have to first.
Oh, yeah.
You have to first have run
Yeah.
the eta program.
Yes, you run this. This part, you mean?
No, I mean, it's a function of eta, right?
Yep.
But you have to first have eta, right?
Yeah, I'm just saying it's 0.1.
All right, I'm gonna want to.
So when you do a power analysis, you're assuming an effect size. So I'm assuming my effect size is this. I'm just using this to convert it to F. But yeah, I'm saying, like, I could have said that this is, so, like, we could try this for a smaller eta value and see what sample size we would need. So let's go over to R. So let's say we had 0.05 instead.
Right.
And so same thing otherwise, 3 groups, power of 0.8. Let's see what sample size we would need. Oh, I didn't run my eta to F. Function that I wrote. Let's do that.
Yeah, that's what I mean. In that function that you wrote,
Yep. So I run this first. Oh,
it says square root of eta over 1 minus eta.
Yep.
Where is it getting that eta from?
So the eta value, this is just a variable. So when you write a function, you're saying this is the variable name. So this is essentially saying what my function does is eta to it doesn't, so it doesn't know what it is. But if, so what I'm gonna say is eta equals 0.05 or 0.05. So that's what it's saying. And then it gives me the output, you see. So eta is just, it's the name of the variable, the name of the argument.
Okay, all right.
Does that make sense?
Yeah, I thought that you had to have first your eta value.
This is saying that I want a generic function that'll take any eta value, and then it'll give me the equivalent f.
Right.
So the eta is just the name of the argument that you input to the function, and then it outputs the f.
Okay, all right.
And so just since I started it, so here we would have needed 60 something, 62 per group to get 80% power for eta squared of 0.05. Okay. So that's just writing what I just said. So the most general case is this power F2 test. So this is power analysis for any linear model, essentially. It takes eta squared for some reason, instead of, I'm sorry, Cohen's F squared for some reason, instead of Cohen's F, which is the equivalent of, you could also, so eta squared and R squared are the same. So you could treat, like if you're doing this in regression, this would also work for a regression power analysis. And you could just use R squared instead of eta squared and convert that to F squared. I don't know why, again, I don't know why it's different. Just is what it is. What we do in this case is we have these U and V are our arguments instead of number of groups and sample size per group. So U is the numerator df degrees of freedom, V is the denominator degrees of freedom. So this is like in our F statistic, we need to figure out what our degrees of freedom are. And so again, we could do essentially the same thing. So let's think through how we do this. So we're going to do an a priori power analysis. We want to determine the sample size. And let's assume it's the same thing. It's still in Anova. We have 3 groups. Eta squared is 0.1. So what do we enter into each of these arguments, and which is the one where we leave something out? So if we're trying to determine sample size, which of these is the one that's going to tell us what our sample size would be? Any guesses? Which one of these? So I'll give you a hint. It's one of the first 2. Which of the first 2 is the one that is like sample size, and which of them is the one? So one of them is related to sample size, and one of them is related to the number of groups, right? So which one is the number of groups? Which one is G minus 1? And which one is N minus G? So the numerator degrees of freedom is G minus 1. So that one we're going to put in G minus 1 because we know we have 3 groups. The denominator degrees of freedom, that's the one we leave out because that's N minus G. Then for effect size, I'm going to just do my eta to F thing again, but I'm going to square it because again, it takes F squared for some reason. And then the other 2 get to stay the same. So this is going to be an equivalent analysis to the one we just did. And so I put everything in here. So how are we interpreting this result? So this is what was output. So how are we interpreting that? What is our sample size going to need to be given that's our denominator degrees of freedom?
There are 3 groups here.
Yep.
You have to divide that by 3.
Nope. Just add 3 because the denominator degrees of freedom is N minus G.
Right.
So all we need to do is if our denominator degrees of freedom is about 87.
But per group.
Oh yeah, we need to. Well, first we need to add 3.
Right.
So we need to. But then divide by 3 per group.
Right.
Yes. So if denominator degrees of freedom is N minus G, then the denominator degrees of freedom plus G is N. So we get 90 as our total N. As you said, 30 per group, which is exactly what we got before. About 30 per group. So it's the same analysis. It's just done a slightly more generalized way. So you can apply that to other cases besides a balanced ANOVA. So for example, if you have unequal sample sizes, you could do it that way. And so one of the reasons that the Anova test assumes equal sample size is because eta squared as an effect size is sensitive to unbalanced designs. So when one or more groups are much smaller than the others, eta squared is going to tend to be smaller than what you'd expect in a balanced case. So the thing is, the statistical power to reject the null hypothesis is still better if you have like some large groups than all small groups. So you still generally want to keep the unbalanced design if that's what you have, as long as you can't balance it out by like making all the groups equal. You don't want to do a smaller balanced design than like a larger unbalanced design for statistical power reasons. But this might underestimate eta squared if you do it this way. So there's sort of like a trade-off that you get where like your effect size might be a little more difficult to interpret, but you're more likely to reject the null hypothesis even in the unbalanced side. So again, power gets a little weird in unbalanced designs. That's why it's always better to plan your experiments with balanced groups. So the last thing we could do is we can visualize the relationship between statistical power, effect size, and sample size with a plot. This is called a power curve. So here is a power curve for eta squared in one-way Anova. The one thing I'm holding constant here is the number of groups G. I could vary that as well, but it's easier to see it. So here, we have G group, we have 3 groups. So each different line represents a different effect size. The x-axis is the sample size, and the y-axis is power. So you can see when we have a small effect size, the orange line, that's 0.01. Our power does increase, but it's a very shallow slope. When we have a very large, even not a super large effect size, even just a fairly large effect size, we get pretty good power even with fairly small sample sizes. And this is the total n, not n per group. So this is, you divide this by 3 to get the per group. So you could essentially have 10 per group, and with eta squared of 0.25, you'd have pretty good power, really good power. Yes, that's how you would visualize the relationship between power and effect size. Let me see. Okay. All right. Any questions before we move on from power? We're going to go back into other areas after this. That'll, in psychology, eta squared 0.25 is a pretty large effect size for an Anova. In other cases, it's not, but you'll have pretty good power to detect it. So like 30 is like somewhere around here. So it's like you have like you have like 90% power with like a 10 per group and 3 groups to detect an effect size that big. But an effect size that big will probably be pretty unusual in like pure experimental design type Anova. Like that's a pretty big effect. Okay. All right. So now we're going to get back into Anova stuff. And we're going to start by talking about pairwise comparisons. We're not going to talk about adjustment methods yet. That'll be next week, but we're going to just talk about how to do pairwise comparisons. So far, when we've done our Anova stuff, we've really only tested if groups are different from one another. We haven't really looked at how they might be different from one another. And so to look at how they might be different, we're going to use contrasts. So contrasts let us check whether there's some, just in more very broadly, whether there's some linear combination of the means of the variables are somehow different from one another. So what to check this, we assign a coefficient to each group mean, and we check whether the total of one group of means is equal to the total of another group of means. There are you can even do more than that. That's the most common thing you'll see. And the most simple on the other extreme, the most simple thing you can do with contrast is to check whether the means between 2 individual groups out of many are equal to one another. So we're going to look back at the wine data we've been looking at, and we're going to check for differences between condition A and the control. So what's our null hypothesis to check whether the control and condition A are different? how would we state the null hypothesis? Yeah. So there are two ways to do it essentially. We could say the population mean of A equals the population mean of control, or you could say that the difference between them is 0. So this is really sort of the easier way to think about it. This is the way the math works down here. So if we wanted to be lazy about this, we could just forget about condition B, and we could do a t-test between the two groups. Why wouldn't we want to do that? Why is that sort of like not an optimal workaround for this? So the reason is because we're wasting good information. So mean square within is, which includes all of the groups, is an unbiased estimate of the population variance. So there's no reason we shouldn't be using that as our criteria for what we expect if there's no difference. So another way to look at it is that the general form of the F statistic is sums of squared reduced minus sums of squared full, divided by df reduced minus df full, divided by sums of squares full, divided by df full, which we can also, in an Anova, rewrite the denominator as just our mean square within. And we still have the same full model here. So we're still comparing, our reduced model is just saying 2 of the means are equivalent. Our full model is saying all of the means are different. So we're the same full model. So we really want to use the same denominator here. We don't want to throw away condition B and get rid of that information from our denominator. So we're better off keeping it the way it is. This is going to be a more powerful test. So what we have to figure out is what the numerator is. So we have to figure out how to understand this. So essentially what our reduced model is, the sum squared for a reduced model. And so for the general case, what we're going to do is we're going to define, this goes beyond just pairwise, but we can do this for pairwise too. So we're going to define a contrast with the letter C. And so this is going to let us define the coefficients we want to use to make up our weighted combination. So in our example, we're using our population means now. So we're getting y bar A and y bar control. And we can define our contrast as 1, 0, and -1. So that's going to essentially say we want 1 times condition A, 0 times condition B, and -1 times control. So then we can define this term psi as the sum of all of our contrasts times our means. So this is just saying exactly what I just said. So it's taking the sum of the differences between the means multiplied by the contrasts. So let's find our group means and define and figure out what psi is for our actual example. I'm also going to save the sample sizes because that'll come up later. So here I'm loading my data. This is the same thing that we've seen a few times. I'm grouping by condition, and then I'm getting the mean of the rating variable, and I'm saving the sample size too. And this is what I get. So I get my means for each group and my sample size for each group. So what we have is our psi value is our contrasts times the means. So if I just plug everything in, I get 1 times the mean of group A, 0 times the mean of group B, -1 times the mean of group C. So this just really is the difference between the means of the two groups. It's just a fancy way of writing it. And the reason we do it this way is because we can use this for more general cases as well, and it works very perfectly adequately for pairwise comparisons. So the other thing we need to account for is the sample size of the groups, which is why I saved them before. I'm not going to go through the proof of why this is the case, but we can get the sums of squares reduced minus sums of squares full, which is what we need for our numerator, by squaring the psi we got, and then dividing by this, which is the sum of all of the, for each group, it's the sum of the coefficient squared, the C squared value, divided by the group sample size. So just plugging in, I have 3 groups. So we get this becomes 3.29 squared, and then this just becomes each of my contrasts divided by the group sample size squared as well. Good.
Go back to one thing.
Sure.
Sorry. On the full model, you said, what does the full model say? That will, each of them are different?
Yeah, so the full model is, so the reduced model in our case is that A and control have the same mean and B has a different mean. So that's our reduced model now. Our full model is A is different from B is different from C and A and control. So it's just in, well, so the full model is assuming that they're all different from the grand mean. In this one, we're saying that two of the mean, in the reduced model, they're saying two of the means are the same.
Okay, I have the full model.
Okay, so in R, I can program exactly what I just showed you here. So first I'm going to define my contrast. I'll call it C1 for my first contrast. I'm going to find my psi value by summing up my contrasts times, these are the means from the object that I got before. So this is exactly what we saw. So this is just the difference between condition A and the control. And then I'm going to take psi squared and divide it by the sum of the contrast divided by the sample size, which is what we saw here. And I'm going to save this. I'm going to call it SSH. You'll sometimes see when you have a hypothesis that isn't just the pure sums of squares between or something like that. So sums of squares between is the hypothesis that each group is different. This is some other hypothesis. We're saying that two of the groups are different. So this is, or one of the group is different from the other two. So a more generic term is that you can use sometimes the sum of squares hypothesis. So that's why I'm calling it SSH. But either way, this is before dividing my degrees by degrees of freedom, this is essentially my sums of squares term for my numerator. So the last thing I need is to divide by degrees of freedom. And so in this case, it actually turns out that our degrees of freedom are 1, and they're always going to be 1. So essentially what we're saying when we're using contrasts in the reduced model is that in this case, we're saying that 2 of the means are equivalent. So instead of estimating 3 means, I'm saying I'm only estimating 2, one for A and control and another for B. But this is actually true whenever you do any kind of linear contrast like this. Because essentially what you're saying in a linear contrast is that if I know each one of my means except for 1, I can determine what that last one is, no matter what. So you're essentially gaining a degree of freedom in your hypothesis here. So the degrees of freedom of the full model plus 1 is going to be equal to the degrees of freedom of the reduced model. So the reduced model is always going to have 1 degree of freedom more than the full model. And then I'm subtracting the degrees of freedom from that to get, if we look back, because that's what we need here. So we need df reduced minus df full. And so, but df reduced is df full plus 1. So we have df full plus 1 minus df full. We just get 1. So it's always going to be 1 here. This is why we will. We'll see why later. What I was going to say. All right. So this is what our formula breaks down to. So sum of squares. This is our general formula here. And so we're plugging in the numerator that we just obtained. We don't need to divide by the degrees of freedom because it's just dividing by 1. And so again, I called my SSH for sums of squares hypothesis, which is what you'll see sometimes. You'll sometimes see in R, an output will say like sums of squares hypothesis. This is what it means. So from my denominator, I need to get my mean square within. We've seen how to calculate mean square within a whole bunch of times. I'm not going to do that every step of the way, every time I teach it. So I'm just going to get it from my output now. I'm going to be lazy about it. One thing you can do if you want to access it directly, and we talked about this a little bit too. Instead of calling summary when you do AOV, you can call little a Anova on AOV. And that's a way to save the output. Then you can access what's inside of that. You can't do that with summary for AOV objects. This is going to get more confusing as we go. So brace yourselves. There's a function that we're going to use later. That's the big A Anova function that we're going to need a lot. That's even more confusing and does a lot of the same things. It's really idiosyncratic but important. But we'll talk about it. Not yet. Either way, for now, I can save my output here as Anova 1. And so what I need to get here is the mean square from residual, which is the denominator mean square. So this is mean square within. Residual is within. So this is my mean square within value. I could just take that and plug it in. But I could also, because I saved this Anova 1 thing, I can get it from the object, so I can access it now because that's saved. So it actually rounds it to 2 digits. This gives me a more precise version of it. Whatever, it doesn't matter. Either way, I'm just, it's a way of getting your mean square within from an Anova output. And so now I just need to divide my hypothesis by my mean square within, and that gives me my F statistic. And so my F statistic here is 6.25. So how am I going to get the p-value? Knowing my F, what's the function? 2 letters, PF. So we're going to use our PF. What are our degrees of freedom? Even if you don't remember the numbers, well, we know the number for the numerator. What's the numerator degrees of freedom? We don't need to know G. It's just 1. Remember, we found out it's 1. So DF1 is 1. What's DF2? If you don't remember the number, it's okay. What is it? How can we say it in letters? It's the same as what we would do for the full. So that's just still n minus G. In this case, it's 155 minus 3. So I'm going to plug in 1 and 152. That's my p-value. And again, now we'll look at the easy way to do it, the way that you'll always do this when you're working on real projects and not learning about it. So there's actually several ways to go about this when you're doing it in the sort of experimental design Anova framework. What you'll often use is this e-means approach. So this stands for expected marginal means, and it lets us do a lot of fun stuff with contrasts. So the package is called e-means, and there's a function called e-means inside the e-means package. So we're going to load up the e-means package and then use the e-means function. And so that's going to give us our expected marginal means. And then on that thing, we have to save what we do with e-means. Then we can use contrasts on the thing that we save. And so it's not as hard as it sounds, don't worry. So this was the Anova I did before. So I'm going to just call e-means on that. And then for specs, I just have to put what the name of my grouping variable is here. This will get more complicated later when we have more than one grouping variable. Right now, we only have one. We're still just doing one-way Anova. So my grouping variable was condition. And so I save this e-means thing, and then I call the contrast function with the output of my e-means. And then, so I have to specify, to input the contrast, I have to specify method, and then I have to call it as a list. And the reason is because sometimes you'll do more than one contrast. Here I'm only doing one. So I'm just putting one object in my list. So you have to do it method equals list, and then your contrast can go inside the list. And so this is my output. And so why is this a T? Not an F? Same p-value. Well, it's not necessarily 2 groups. Sometimes we might be doing things combining other, we might be referencing all 3 groups. What was our numerator degrees of freedom? 1. Anytime your numerator degrees of freedom is 1, and F and a T are equivalent. It's just that F is T squared. So that's a little different because of just rounding, but like it's the same thing. That was our T value. I squared it. That recovered our F value. So usually you'll just write it as a T, not an F. So condition A was significantly different from control. And write it up in APA. So the last thing for this section, we can also use the pairs function. And so we don't have to write any contrasts if we do the pairs function. So if we do this will give us all pairwise contrasts. But why might this be dangerous? What's going on? You've probably seen something like this before where you've done something else in addition to be a little extra cautious. Anyone know what I'm talking about? When you do multiple comparisons between groups. Yeah, right. So you have to do some kind of adjustment. You should do some kind of adjustment like Bonferroni, which we're going to talk about more next week. Right, when you're just looking at one contrast, you don't need to worry about that. But if you're looking just at all pairwise contrasts, there's a few extra things you should do to ensure that you're not making extra type 1 errors. All right. There's one more set of slides on some more complicated stuff. Before that, let's take a break. 10 minutes. It's 10:23. So 10:33, we'll jump back. So the numerator is 1 because anytime you do a contrast like that, where the contrasts equal 0, essentially, what you're saying is that if I know, like, let's say I have 5 groups and I'm comparing like groups 2 and 3 to 3, 4, and 5. We'll look at more complicated contrasts in a second. You're still saying that if I know any 4 of my groups, I can figure out the 5th one. So you have 1 extra degree of freedom. So you're saying that like any one of my means can be determined if I know all of my other means. So that's why degrees of freedom is 1. Does that make sense? Sort of, a little bit.
Yeah.
I changed my setting to choke output in crystal.
Oh, I always forget to do that. I only learned about that from Leah this semester. I didn't even know about that.
Oh, I just want my output.
I know. It always annoys me when I got used to it. In our when you use our markdown, you mean, right? Yeah. No, I didn't even know about that until I TA'd for Leah this semester. She showed me.
And I want to change the setting as a default.
Well, the thing that I always do is I move. So the one thing that I always change when I install R is I move the console. I switch the console in the environment because for me, I almost never look at my environment. Honestly, some people do, but I almost never look at. So that way I can just have my script be like one big screen. So like I'll switch it back after, but I do. So this is, I have it like this. So my console's up there. This is how I like to set it up. That's just me because I almost never look at this stuff, like the stuff down here. Get out of here. Like this stuff I almost never use. It's useful too. I should use it more, but I just never do. So this is just the way I've always done it. But I'll switch it back because this isn't my personal computer.
How many students in the lab?
14, I think. I took that class with Haining a long time ago.
How was it?
It was good. He was good. Have you taken classes with him yet? Wow. He's good. He's a really good teacher. I've taken so many classes with him. I've had him for like by far the most number of classes. Yeah, he's good.
He's my mentor. I didn't take any.
You'll take SEM with him next semester,
Yeah.
and then HLM again with him.
Mark, whom
Yeah.
are you talking about?
Hayning.
Sorry for interrupt. Ah,
He's busier now because he's the program director. He wasn't. He didn't used to be. When I started, it was Dr. Kim. So many classes have I taken? Four? I like this. Maybe I've taken more classes with David at this point. Taken at least 4 from Hayning. Yeah, I've taken 4 with David too. So maybe it's the same. 2 with Leah, 1 with Kim.
Oh, you only take one class from the paper.
Regression. When I was taking it, when I was doing it, they told us not to take his. Well, I think he was on sabbatical that semester too. But he just told me to skip his multivariate class and just do the advanced one. They were making all of us do it back then. But they got a lot of pushback because they made some of the ADP students do that too. And that was not a good idea because it was way too hard for them to do that. It was hard for me. That was a hard class, the advanced multivariate class, especially at the beginning. It got easier as it went, though, right? The end was easier in the beginning, right?
Yeah. And then
Well, the beginning is all that linear algebra, so there's only so much you can do in the lab.
take one or two examples for that.
Yeah, I should probably take a calculus class at some point just to refresh on it because I don't remember any of it from when I took it. Honestly, I wish they'd give like a more like probability focused class. That would be good, especially for Bayesian. That would really, really helpful for Bayesian.
I didn't major that night. I took chemistry before.
I majored in psych, so Give Randy another minute, then we'll get started again. All right, I'm gonna keep going. She needs to catch back up. Okay, so the other thing we're going to talk about today is more complicated contrasts. So pairwise contrasts are very intuitive. They're often likely to be of theoretical interest, so we use pairwise contrasts a lot. But we can do a lot more with contrasts. So for example, let's say we wanted to test whether the average experimental effect in our wine study again differed from the control group. So we wanted to test whether groups A and B were different from control. How would our contrast look for something like that? It's okay. Anyone want to guess what the contrast would look like? So for when we tested A against control, we did 1, 0, -1. What would A and B against control be? Yeah, 0.5, 0.5, -1. Yeah, exactly. So we could have our two experimental groups get contrast at 0.5 and our control group get -1. So essentially what this is saying is that the average value of the two experimental group means. This is the same as saying group 1 plus group 2 divided by 2. So it's just saying the average between them is the same as the control group. So it's a bit easier to sort of learn about this stuff when we have balanced sample sizes in the when we're doing more complex contrasts, which we'll see a little bit later. So I'm using a slightly different simulated data set for this one. And this time each group has n equals 40. So there's the same number of observations in each group here. You can use more complicated contrasts when the groups are unequal, but the math gets messier. And I'll show you some of that, but it's much easier to understand if we look at balanced groups. Let's do the same thing we did before. So I'm going to load up my data. I'm going to get the means of each group, and just to show that the sample sizes are equal here, we see that each group has n equals 40. The means are a little bit different because it's slightly different data. Same idea. And so I can test my contrast the same way that we saw using the e-means package, just by defining my contrast and entering it into the contrast function. The math so far is exactly the same as what we saw when we did the pairwise contrast. The only difference is that the contrast is different, but like everything that we did in the last slide really applies here. So I'm not going through the step-by-step math again. And so here we test our contrast, and we see that our average experimental effect is different from our control group. So that's our result. And so one thing to be aware of when we're doing contrast and we're doing like a lot of comparing different types of contrast is that Sometimes all the information contained by one contrast will be defined by the others. So for example, when we do all pairwise contrasts, we really are doing the third contrast is defined by the first two. So if we know what the difference between groups 2 and 3 and 1 and 2 are, or if we know the difference between 1 and 2 and 1 and 3, we also know the difference between 2 and 3. So if we know the differences between any two, we also know the third. So this is the idea of linear dependence. So we can just show this easily. So I'm going to create 3 different pairwise contrasts for all pairwise contrasts. And I'm going to find what the sum of the contrast is. So these are just the differences between each pairs of groups. And so if I I can get my difference between groups 2 and 3 by looking at the difference between groups 1 and groups 2. That sort of makes sense. So I'm recapturing this 8.4, which is the difference between group 2 and 3 by knowing the difference between group 1 and 2 and the difference between group 1 and 3. So if I know the difference between 1 and 2, which is this value, and 1 and 3, which is this value, I also know the difference between 2 and 2. So that's the idea of linear dependence. So sometimes one contrast will be fully defined by all of my other contrasts. It can be tricky to like formally prove linear dependence in very complicated scenarios. It's easy here because we have simple contrasts. Sometimes it's possible to come up with really complicated contrasts that turn out to be linearly dependent. So we're not going to go through that whole proof. It's not that important. It's good to know that sometimes you'll have linear dependence. What's a little bit more informative and interesting are what are called orthogonal contrasts. So the idea between orthogonal contrasts isn't just that they're linearly independent, but they contain no overlapping information whatsoever. So the information from one contrast is completely orthogonal to the information from another contrast. So for example, we could say compare condition A to condition B, and then we could compare the average of condition A and B to control. These are orthogonal contrasts. What we're saying is that they're orthogonal because the comparison implied by the first contrast has no bearing on the result from the second contrast. There's no information contained in the first contrast that is also contained in the second contrast. Any questions so far? Okay, so this is where the equal sample size thing comes up. So when we have equal group sizes, checking for orthogonality is fairly trivial. Essentially what we need to do is multiply each contrast by its sister contrast. So like we take the two contrasts and multiply each element of them by the element of the other contrast, and then we sum that up. And if that sums to 0, the two contrasts are orthogonal. And we'll look at an example to make this a bit more concrete. So in the cases where we don't have equal sample sizes, we have to divide this by the group sizes. And again, this gets a little bit hairy to like go through the math of, so it's not really worth going step by step through it. Just know that this is the definition of orthogonality when you have unequal groups. So let's take a look at the example that I showed before to prove that these two contrasts are orthogonal. So first, I'm just going to line them up on top of each other so we can see them next to each other. So essentially what I need to do is I need to take the product of this and this, so 1 and 5, or 1 and 0.5, then -1 and 0.5, and 0 and -1. And if the sum of those products is 0, my contrasts are orthogonal. So the first product is 1 times 0.05 is 0.05. The second product is -1 times 0.05 is -0.05. The last one is multiplied by 0, so it's a 0. So 0.5 minus 0.5 is 0. So therefore, my contrasts are orthogonal. Does that make sense? Any questions? So easy to do in R. So if I have two contrasts, I just multiply them together. And then I take the sum of what I multiply together and I check if that's 0. So here I'm just multiplying them together and getting what I got before, 0.05 negative 0.05, 0. Then I just sum it up. It's 0. Easy peasy. So any ANOVA, when you have G groups, you could have many different sets of orthogonal contrasts. So you can have like lots of different pairs of orthogonal contrasts, but for any set, you can only have up to G minus one. So any single contrast can have up to G minus two additional orthogonal contrasts to it that are also orthogonal to one another. So one way to think about this is that when you have a set of G minus one orthogonal contrasts and you apply them to an ANOVA, you're using up all of the information in the ANOVA to test the maximum number of unique contrasts. And there are different ways you can structure the contrasts that'll use up this information. But this is essentially a way of saying like, this is the most amount of independent information I can get about my ANOVA. So we're gonna look at an example. So these are what are orthogonal. These are when we have three groups, the maximum number of orthogonal contrasts we can have is 2. So these are orthogonal contrasts, 2 orthogonal contrasts. We can't have another third contrast that is orthogonal to both of these. So this is what it might look like if we were testing our orthogonal contrasts in R. And so we would say condition A and B were different from one another, and then the average of conditions A and B were different from the control, is the way we would interpret that. So let's imagine we add another condition, so that way we have 4 groups. That way we can just think a little bit more about what orthogonal contrast would look like when we have more groups. Give this a try. Are these two sets of contrast orthogonal to one another? No, they are not. So when you add them up, you get, when you multiply, add them up, you get -4. So what's one thing we could do where we could, how might we tweak one of, there are different ways you can tweak these, but there are some really simple ones. What's a way we could tweak one of these contrasts to make it orthogonal to the other one? So first, let's think about what's going to happen to the middle, right? The middle, since there's zeros on the bottom, those are always going to zero out, right? So what do we need to do to make it so the two outside parts cancel each other out? Yeah, that's the idea. So, right, so if we switch one of the negative signs to the middle and make the n positive, right? So if we take the, or if we do it the other way around, as long as the ones on the outside are different from the ones on the inside, then you'd have -2 plus 2, or 2 plus -2 gives you an orthogonal contrast. So here I just take it and I make it so the middle one is -1 instead of the end one. See that?
Still testing the same thing.
No, this is a different hypothesis now, but I'm just
Yeah.
defining a different, I'm just figuring out how I could get 2 different contrasts that are orthogonal to one another.
Right. But we're not able
It's different hypotheses.
Right.
And so these would be orthogonal.
Now, so then, so let's say there are 3 groups, that there would be 2, there can only be 2.
There are different sets of 2 you can have,
That's
but
what I-
any
yeah,
any
that's
set
right.
can have up to 2 orthogonal
Right,
contrasts.
but you can have multiple sets too.
Yeah. So here we can have up to 3 orthogonal, because now we have 4 in this example. So we could have up to 3 in any set of orthogonal contrasts. What about these? Orthogonal or not? Guess no? Yeah, right. This is actually a very common type of orthogonal contrast. So this is essentially saying we're testing one group against the remaining group. We could actually add a third contrast to this, which would be just 1 and -1 in groups 3 and 4. So this would be the first group versus the other 3, the second group versus the remaining 2, and then we could do the third group versus the fourth group, and that would also be orthogonal. That's a common type of orthogonal contrast you'll see. And so that's all I have on orthogonal contrasts. The homework is up on Blackboard now. It's got a little bit on each of these 3 sections. So here's the homework. So you've got some questions on power analysis. These don't require any data, they're more conceptual. Then a set on contrasts, which includes some pairwise contrasts and some questions about orthogonal contrast. And then the extra credit is asking you to write a function that will test a set of orthogonal contrasts and tell you whether they're orthogonal or not. So this is a little complicated. So this is what function will look like. So you'll name the function all orthogonal. It'll be take one variable, which is some matrix of data, and then it'll do some stuff, and it'll tell you if each set of contrasts here is orthogonal. So here, this is the set that we just looked at. So 3, -1, -1, -1, then 2, -1, -1, and then the last one is 1, -1. So this is orthogonal. So it should report that this is true orthogonal. And then this one is not. So it should report this one is false. And if you can even get it to tell you which ones are not orthogonal, even better. Again, tricky. This is tricky. This will test your programming skills a little bit as much as your statistical skills, but it's good practice. So, and it's extra credit, so no obligation to do it. And so any questions before we wrap anything up? All right, that'll be live for today. Stop the recording just for the